All right, welcome to part 2 of our series on solving some equations. Now we're going to take it up a notch, right? And instead of just ax plus b equals c, we're now going to have ax plus b equals cx plus d. We're going to add in some parentheses, and then we're going to jump into some more applied problems because it's always good to practice these things with some word problems. Okay, so let's look at our next level. Ax plus b equals cx plus d. Well, we remember that our ultimate goal is to have ax equals b, right? We want just one x, one amount of x, ax equal. Ultimately our goal is to have x equals b. If we have ax equals b, we divide both sides by a. If we have ax plus b equals c, we move the b across, then divide by the a. When we have ax plus b equals cx plus d, we move the b across, move the cx over to the left, and then divide by, so we're doing the same thing, we're just adding in an extra step. Simple example, right? Combine like terms on each side of the equation, nothing to combine. Isolate our variable of interest. In this case, we want to isolate x. So I want to get all of our x's on one side. Now, in this example, I'm holding true to what you guys have seen a million times, which is keeping the variables on the left-hand side. But in my opinion, this is a bad thing to do in this example. You should have instead moved the 2x over to the right because you want to keep your variable positive whenever you can, right? So in this case, when we move the 5x over, we have to subtract 5x from both sides, and we end up getting a negative 3x. Now, it's not that big of a deal when we have an equation, but what happens when this is an inequality? What if this started off as 2x plus 3 is less than or equal to 5x minus 9? Right now, with this last step, what's the last thing we have to do? We have to divide both sides by negative 3 to solve for x. And when we take negative 12 divided by negative 3, the negatives cancel, and we get positive 4, right? X equals positive 4. Simple, easy. But what would have happened if originally the whole thing was less than or equal to, right? Then we get down here, and we have negative 3x less than or equal to negative 12. You divide both sides by negative 3, and you have a 4 here. What do you have to remember to do with the sign? When you divide by a negative, it changes directions, and that's something that people forget. They mess that up all the time. If instead you would have kept your x's positive and you would have kept them on the right-hand side of the equation, then at the end you would have had, on the left would have been 12. You would have had 12 equals 3x. Then instead of dividing by negative 3, you would have divided both sides by positive 3, and you wouldn't have to change the direction of the sign, and you would get x is greater than 4 without any problems, right? Because remember, they'd be switched. So now you would have 12 is less than or equal to 3x. And then when you divide by both sides, you get 4 is less than or equal to x, which is the same thing as saying x is greater than or equal to 4. So another piece of advice, try to keep your variable positive whenever you're doing this work. It doesn't matter so much at all when you have equalities, but when you have inequalities, it can bite you in the butt because you could forget when you divide by a negative, you got to flip the sign. Here's another example. And again, we're keeping the x on the left, and it ends up being negative, and that's the wrong thing to do, guys. This is how the book keeps doing it. These solutions, these equations, examples, are taken straight out of the book, and you can see that even this book is doing that stupid old habit of always keeping your x's on the left. Let's see how, more difficult it is. You'll see that it's not. To do it the other way. I've got 8 of them here, 4 of them here. You know what? I'm going to keep them positive. I'm going to subtract 4x from both sides, and I'm going to have negative 5 equals 4x minus 7, right? Because 8x minus 4x. Now, I want to keep the x here, so I need to move the 7 over there. So I'm going to add 7 to both sides. And 7 minus 5, isn't that just 2 equals 4x? Yeah. Okay. Now, to solve for x, divide both sides by 4. And I get 2/4, which equals 1/2, equals x. Isn't that a lot easier than having to do minus 2 divided by negative 4? You got to remember that minus 2 divided by negative 4 is now positive 2/4, which is positive 1/2. Ugh. Again, more places to screw up, especially if it's an inequality. So guys, stop doing this. Stop keeping your variable on the left and instead start keeping your variable positive. Much, much easier. Okay, how about solving an equation containing parentheses, our second, right, objective? So when we have parentheses, we want to get rid of those. Remember, step one, get rid of fractions, decimals, and grouping objects. And grouping objects are parentheses. You get rid of parentheses by doing the distribution. We know that we have to eventually get x all by itself. And the only way to get x all by itself is to rescue it from within grouping objects. So if your grouping objects are parentheses, you got to do the distribution property. If your grouping object is absolute value symbols, then you've got to do the trick for getting rid of absolute value symbols. It's a pretty easy trick. I don't want to talk about it here because I don't want to confuse you, but it's very easy. You just get an or kind of thing. You solve the equation two ways. If your grouping object is a square root, right? You've got the square root of 2x plus 3 equals a bunch of stuff. Well, how do you get rid of a square root? Duh, you square it. So you square both sides of the equation, and that gets rid of that, right? So these steps, these basic steps I'm giving you, can be applied to more and more complicated equations, as long as you just understand that all that happens is to get rid of that grouping object might require a separate skill depending on what that grouping object is. In this case, it's parentheses, so all we have to do is the distribution property. So we're going to distribute the 5 through, get 10x minus 15. Over here, we distribute the 3 through, get 12x minus 3. Again, this stupid book always wants to, keep everything on the left side, and I would not do it that way. I would move the 10 over. So instead, I'm going to do it this way, and I'm going to subtract 10x from both sides to keep it positive, right? So we're going to get negative 11 equals 2x minus 3. Then we're going to add 3 to both sides to get negative 8 equals 2x. Then we're going to divide both sides by 2 and get negative 4 equals x. In my opinion, a lot easier, a lot less chance of making mistakes than doing it this way, where you've got to divide by a negative and all that kind of stuff, and then you'd have to worry about flipping the signs if it was an inequality. So once again, always keep it positive. How about another example? Do the distribution. Remember here's where it gets tricky. This is a negative 4, so you have to distribute negative 4. So now it's negative 4 times everything. Negative 4 times 2 is negative 8. Negative 4 times negative x gives you positive 4x, right? Here's positive, it's easy, 3x minus 6. Combine like terms on each side of the equation. So we're going to put the 3x and the 4x together, get 7 of them. We're going to put the negative 6 and negative 4 together, get negative 2. Now we've got negative 7, 3. So now we put things on the left and it stays positive, right? So it's okay to keep them on the left this way because it stays positive. Now we have 4x minus 8 equals negative 10. Add the 8, 4x equals negative 2, divide by 4, x equals negative 1/2. What's the one thing we haven't been doing with any of these equations that we should have been doing? Hopefully you're all screaming at the screen. Check your answer. That's right. You should have taken the negative 1/2, plug it back in here, and make sure it works. Same thing with our previous examples. Whatever the solution was, right, negative 4, we should take negative 4, plug it back into the original equation, and make sure that it works. That's a way to check to make sure we haven't made any mistakes. All right, let's finish up with some application problems. A lever system is shown below. A lever is, a fulcrum with a balancing system. You can think of it as like a teeter-totter. If you've ever seen those, if they even exist anymore. But basically something that's balanced on a pivot point. So you've got a lever or a bar and a fulcrum and two forces, F1 and F2. So two things that are pushing down on each side of the lever. The distance D represents the length of the lever. So the full length of the lever is D. And X represents the distance from F1 to the fulcrum. So you can see everything's been labeled in the picture. And if that picture wasn't given to you guys, the very first thing you should do is draw that picture and label everything they tell you. And your picture should look basically like that, right? You got the d for the total distance, x going from F1 to the fulcrum, being the little pivot point, and then you can figure out this distance obviously is d minus x. Okay, so there's a principle of physics, one of the kind of the laws of physics types of things, that states that when the lever system balances, we know that the force, F1, times the distance from this fulcrum has to equal the force on this side times its distance. So you can see that as the distance x gets much bigger than this remaining distance over here, doesn't this force have to get a lot smaller, or vice versa? I mean, if we look at this picture, smaller distance, bigger force, right? Larger distance, smaller force. That's how a lever works, right? If you try to lift something that's super, super heavy that you can't lift on your own, you put this fulcrum much, much closer to this edge over here. And now big distance means times little force gives you little distance times big force. So now every, foot-pound of pressure you can push down on, you're going to get a lot more lift in this direction. So that's how a fulcrum works. That's how you're able to lift things that you normally couldn't. Here's a simple example. 50 pounds on the left, right, 100 pounds on the right. A lever is 15 feet total, so that's our little d. A force of 50 is applied to one end, and a force of 100 is applied to the other end, so there's my picture. Where is the fulcrum located in order to balance the system? So we don't know this distance x, and therefore we don't know d minus x. But we have all the other bits and pieces, so all we have to do is plug in what we know. We're given the two forces, we're given the total distance, and we have this lovely little equation we know of the one force times its distance equals the other force times its distance. Plug in everything you know. Small force times x, larger force times 15 minus x. Now, by the way, did it matter which one was x and which one was 15 minus x? Absolutely not. You'd get the exact same answer if you set it up, with this being x and this being d minus x versus the one on the right being x and the one on the left being d minus x. All that's going to happen is they're going to trade places, right? So in this case, when we do the math, do the distribution, move the 100 over to keep it positive, not to put it on the left, but to keep it positive, divide by 150, we get x equals 10. So according to this picture, this distance is 10, and this is d minus 10. 15 minus 10 is 5. If you had done it the other way and made this x and this d minus x, all that would have happened is your x would have ended up being 5, and then the other one would have been 15 minus 5, which would have been 10. You get the exact same answer. As far as the picture is concerned, your x would be different, right? So it doesn't matter. So don't panic about, oh, which one do I let be x and which one is d minus x? Doesn't matter. Draw the picture, label it, jump in, go for it. You're going to get the right answer as long as you don't make any math mistakes. Okay, so that's it, guys.